That's a clicker.
It is working, yeah? Okay. Let's continue with this second impressive lecture about natural kinds. We have Pieter Thyssen, and his lecture is Are Acids Natural Kinds? Pieter, the floor is yours.
Yeah, thank you. Perfect. Good. Well, first of all, it's a real pleasure being here. So thank you, Olympia, Hernan, Jesus, Camilo, everyone here for hosting us and having us in Buenos Aires. Yeah, let me jump straight into it because I have quite a lot to say. So as Marabella already said, natural kinds are typically taken to carve nature at its joints. They're not invented. They're discovered out there in the world. They're real, mind-independent distinctions in nature. Now, biological species were long held to be paradigm examples of natural kinds, but are no longer. But chemical species are still widely held to be paradigms of natural kinds, despite sustained efforts by various philosophers of chemistry to the contrary. And that's how I kind of got into this field, being very skeptical about the natural kindhood of most chemical substances. Funnily enough, I already admit straightforwardly now, I'm going to end up being a big advocate for the natural kindhood of acids. Now, most discussions have actually focused on the kindhood of elements and their compounds, such as the two famous examples of gold and water. But a question that I want to entertain in this talk is, are acids natural kinds, or are they merely relevant kinds? And so although acidity has obviously been one of the oldest and most important concepts in chemistry, surprisingly little ink has been spilled on the natural kind question. Now, I'm going to approach the question from the perspective of microstructural essentialism, which is probably also the most critiqued version of natural kinds, but also the one that has been most discussed and most entertained in the philosophy of chemistry. So very briefly, it combines two theses. The thesis of essentialism says that all members of a kind share a common essence, a common set of properties that is causally responsible for all the other observable properties. Microstructuralism as a thesis says that chemical substances ought to be individuated by their microstructures as opposed to by their macroscopic behavior or properties. And so the combination of these two leads to microessentialism, the idea that the essences of chemical kinds are microstructural. It's the microstructure of a chemical substance that makes that substance what it is. And so again, to quote the two most famous examples, the essence of gold is its nuclear charge. Having 79 protons in your nucleus makes you into gold. And the essence of water is its molecular structure, being composed of H2O molecules. Good. So given that outlook, in order to be a natural kind for the scientific essentialist, all acids would have to have a common essence, a common intrinsic property or a common structure. And this idea actually resonates particularly well with the early views of acidity, which were all constitutive. And so Lavoisier very famously argued that all acids are composed of oxygen. They have oxygen in them, and that is what makes it an acid. Oxygen therefore literally meant acid generator. Later on, Humphrey Davy, but also Liebig, argued that acids are not composed of oxygen, but of hydrogen, but they have this kind of acidifying principle, this kind of common essence that makes them acids. Today, however, most views of acidity are not really constitutive, but are much more functional. Acids don't have a shared ingredient, but they have some kind of shared function. So according to Brunstad and Lowry, acids are proton donors. Their job is to donate a proton. And according to Lewis, acids' job is to accept a pair of electrons. That's their function. So in a few papers, Alex Manafou argued that the Brunstad, Lowry, and the Lewis definitions of acidity pick out acids not by referring to their microphysical structure, but by referring to their behavior in relation to other chemical substances. And Robin Hendricks similarly refers to acids as a class of chemical substances that are grouped together not by some shared ingredient, but in virtue of sharing a pattern of chemical reactivity. So perhaps it would be better to refer to acids as functional kinds, kinds whose members share a common function rather than an underlying essence. The problem, though, is that the nature of functional kinds introduces two important challenges for the micro-essentialist. There is a challenge of multiple realization and the challenge of multiple determination. So with the first challenge, multiple realization, you will see that one function can be realized by many different microstructures. That's the challenge I will be focusing on today. The challenge of multiple determination says that one microstructure can actually be responsible for many different functions, which is a challenge I'll not talk about today, but I'm happy to go into during the Q&A. So multiple realizability, very shortly, is a common feature of many functional kinds. And to give you a very simple example, consider the functional kind predator. So all the members of this kind are grouped together because of something they do. Yeah, they all hunt for prey rather than because of something they share, some kind of underlying essence. As a result, very different species of animals can belong to the predator category, such as jaguar, human, rattlesnake, or stork. That is, the kind predator is multiply realized. Yeah? Now, according to Alex Manafou, since acids are functional kinds as well, they too must be multiply realized. Yeah? And that's going to be the claim I want to challenge. I'm going to claim instead that acids are uniquely realized. There is no multiple realization at play when you consider acidity. Good. But let's get a bit more deeply into what Alex Manafou said. So he says an important consequence of this alleged multiple realizability of acids is that the property of being an acid does not reduce any longer to any given microstructural property. To be a bit more specific, while token reductionism may still hold true, type reductionism clearly fails. Now, so acidity as a property type can no longer be identified to any given microstructural property. And Robin Hendry similarly argued that microstructuralism clearly fails for acids, since no microstructural feature unites all acids and all bases. So the microessentialist goal then of identifying all acids by some kind of unique microstructure ultimately fails, according to these authors. According to Alex, acidity is not discernible at the lower level. It actually emerges out of microphysics and becomes visible only at a higher chemical level as a pattern of chemical behavior. Good, but are acids really multiply realized? So contra Manafou and Hendry, I will argue that acids are uniquely realized at the microstructure level, and thereby I hope to lend further support to the microessentialist project. I'll briefly consider Manafou's argument for the multiple realizability of acidity, and then I'll look at Robin's argument for it. So according to Manafou, acidity is multiply realized because, and I quote, it can be realized by many different systems of electrons and nuclei. So for example, hydrochloric acid, sulfuric acid, and nitric acid are all acids despite having different microstructures, despite being different systems of electrons and nuclei. So clearly this is a case of multiple realization. Different substances all can share the same function of acidity. Now my reply would be that not all microstructural variation counts as evidence of multiple realization, because not all differences are relevant differences. As Polgar and Shapiro in their famous book, the Multiple Realization book, wrote, variation is everywhere in nature, but multiple realization is not. So to explain this a bit better, according to these authors, multiple realization occurs if and only if two or more systems perform relevantly the same function, but in relevantly different ways. And so they give the example of a corkscrew to open bottles of wine. That is a functional kind, yeah, because its job is to open bottles of wine. And it's a functional kind that is multiply realized because a double lever corkscrew and a waiter's corkscrew, they do the corkscrew job in fundamentally different ways. But if you would take two double lever corkscrews, one of which is blue and the other one is green, that wouldn't be a case of multiple realization because there's no relevant difference in the way they perform their function. Good. Well, in the same way, HCl sulfuric acid and nitric acid, they all do their acidic job in the same way. They all rely on the same kind of proton releasing mechanism in order to exhibit their acidic behavior. So this is actually not a case of multiple realization, contra Manafus' claim. So let me quickly move on to Henry's argument for the multiple realizability of acidity. According to Robin Hendry, the problem is how to extend the acid category from these core examples that I just mentioned to all the other examples of acidity, to provide necessary and sufficient criteria for all cases of acidity, whether in compositional, structural, or functional terms. And according to Hendry, in the history of chemistry, all such attempts have actually failed. Now, although Hendry leaves it mostly implicit in his papers, he appears to be referring to the alleged conflict between the Brunstad-Lowry and the Lewis theories of acidity. Because according to Brunstad-Lowry, acids are proton donors. Their function is to donate protons. But according to Lewis, acids are electron pair acceptors. So at first sight, this certainly comes across as a case of multiple realization. Yeah? They realize their acidic function in very different ways. Brunstad-Lowry acids do so by donating protons. Lewis acids do so by accepting electron pairs. Yeah? So two relevantly different microstructural mechanisms appear to be in play in order to produce relevantly the same acidic behavior, as I just said. So according to Ian Hacking, for example, there is actually not one natural kind, but there are two natural kinds. You have Brunstad-Lowry acids and you have Lewis acids. And so since Brunstad-Lowry and Lewis proposed their theories of acidity in 1923, a bifurcation of the acid kind occurred in that year. And we now have to deal with two natural kinds. Klaus, Rutenberg, and Avi Metz concurred more recently that the protonists, the advocates of the Brunstad theory, and the electronists who defend Lewis's theory, they may be using the same word, acidity, but they actually mean very different things. However, and here comes my counter argument, when you look at them from an electronic standpoint, both theories actually picture the reaction between an acid and a base in the same way. Yeah, so consider the reaction between H3O plus and OH minus. You can see that H3O plus is acting as a proton donor by accepting an electron pair, and OH minus is acting as a proton acceptor by donating an electron pair. So the proton transfer mechanism of Brunstad-Lowry is actually completely equivalent to the electron pair transfer mechanism of Lewis. And so what looked like a case of multiple realization really is a case of unique realization. Now, that is, of course, not to say that the Lewis view is identical to the Brunstad-Lowry one. Instead, the Lewis view is typically taken to be a generalization of the Brunstad-Lowry one. So Hacking, for example, explains that the Brunstad-Lowry definition and the Lewis definition, they happen to agree about bases, but not about acids. Yeah? For example, boron trifluoride is an acid on the Lewis view, but is no Brunstad acid because it doesn't have any protons to donate. Hendry agrees that many definitions of acidity do not co-refer, but all of that doesn't have to be a problem. Yeah? Most essentialists don't allow cross-cutting categories, but they do accept overlapping classifications when they are hierarchically ordered. Yeah. So very briefly, according to the hierarchy argument, no two natural kinds may overlap or have instances in common unless one includes the other. Yeah, and this is exactly the case here. Most chemists maintain that the Lewis definition encompasses the Brunstad-Lowry one. And so they consider the former to be a generalization of the latter. And this is typically referred to in this way. Yeah, this is a typical Venn diagram. So you can see that Brunstad-Lowry acids are a specific kind of Lewis acids, namely the proton donating kind. Yeah? And so there is overlap between Brunstad-Lowry and Lewis, but the former is clearly a subkind of the latter. That's the idea. Now, to end, I briefly wanted to go back to a well-known paper that was written by Hassog back in 2012, who actually took issue with the classification I just show you here now. And he raised a very interesting point. According to Hasso, the Lewis and the Brunschett-Lowry definitions indeed refer to two different sets of chemical substances, and there is an overlap between the two sets. But importantly, according to him, one is not a subset of the other. And he gave a very interesting example, namely the one of hydrochloric acid. And so he says hydrochloric acid for Brunschett-Lowry is an acid because it is a proton donor. HCl can donate a proton. But HCl cannot accept an electron pair as Lewis wants. And so HCl is actually an acid-base adduct of the real acid H plus and the base Cl minus. Yeah. So what is acidic according to Lewis is the H plus ion, not HCl, yeah, which is contrary to the Brunschett-Lowry concept. Jensen agrees that Brunschett acids are not Lewis acids. Finsten and Richmond also agree that Brunschett acids are not Lewis acids. And so Hasso concludes, based on this and other examples, that there is actually no unified theory of acids. So the succession of acidity concepts does not constitute a straightforward progression of increasing generality, with each new concept completely encompassing the previous one. Instead, according to him, the relationship between them is closer to incommensurability than to reduction. Yeah? The history of acidity actually shows how a natural kind can become fractured or bifurcated, as Ian Hacking called it. Now, that is a conclusion I want to resist, and with this I will end. Chang's Mariatic concerns are not new. They were actually raised already by multiple chemists in the years just following Lewis's publication. And so very briefly, the worry was that since the hydrogen atom in HCl already has a filled 1s orbital, it cannot accept an electron pair. For this, HCl first has to dissociate into H plus and Cl minus. And then in a second step, H plus can accept the electron pair from water to form a coordinate bond. And so according to Brunschett-Lowry, HCl is the acid because it donates a proton. But according to Lewis, H plus is the acid because this is what is accepting the electron pair. Now, as Luder and other chemists observed, H plus is actually notoriously unstable, and so it doesn't exist unsolvated. So hence, what actually happens is that the ionization step here takes place simultaneously with the formation of the coordination bond. And so what you get is this kind of reaction where HCl is both proton donor and electron pair acceptor, which shows that Lewis is an improvement upon Brunschett-Lowry and that it is broader, more encompassing, and more general. Going to my conclusions, where does this leave us with respect to our initial question, are acids natural kinds? Well, since Lewis encompasses Brunschett-Lowry, the different concepts of acidity do not cross-cut. And so contra Ian Hacking, Hendry, Chang, Rutenberg, and many others, I want to maintain that the hierarchy requirement here is actually met. What is more, given the equivalence that I showed between the proton donating and electron accepting mechanisms, I think that the property of being an acid is not multiply realized, but is actually uniquely realized, contrary to what Alex Manafou has argued. And so as Tantilo and Seaman in a recent paper have shown, acidity as a property type can be identified with a microstructural property, namely with the presence of a lowest unoccupied molecular orbital or another low energy empty orbital that is able to accept an electron pair. So yes, according to me, acids are a natural kind, even for the microstructural essentialist. Thank you very much.
Okay, thank you, Peter. Now we have some time for questions. Someone here in the audience? Maybe our friends in the Zoom, if someone has a question, is the time.
Looks like
there's a complete silence.
Hello. So thank you for the talk. So your argument seems to rest on the notion of relevant difference, right?
yes,
What are
multiple realization. Yeah.
right. So, and who gets to choose those? or why are they chosen? Why is one relevant difference more important than another, or worth
Sure.
talking about?
Yeah, sure. So I mean that. So the book that was published by Polgar and Shapiro, which is the result of years and years of work on multiple realization, is trying to make the case that multiple realization is not as common as philosophers have taught it to be. Because, as they say, having just a bit of variation is not enough to be speaking of multiple realization. Having a blue and a green corkscrew doesn't count as proof for the multiple realizability of corkscrews. And so they point out, and I think very correctly so, that of course you want something to perform the same function, so they have to be relevantly the same, but the way they perform that function has to be relevantly different. Yeah. And of course, the whole book then goes into, well, what does it mean for something to be relevantly different? Typically, it's going to be using a relevantly different mechanism. Yeah. And so a double lever corkscrew is actually going to use a very different kind of physics in order to pull out a cork than a waiter's corkscrew. And in the same way, I think Robin Hendry and others felt that somehow the way branched acids behave as acids or perform their acidic functions is going by a very different mechanism, a fundamentally different mechanism than the way a Lewis acid would.
So what is the mechanism of the trigger?
Why is mechanism the trigger?
Why is it the mechanism that makes it?
That would be the definition to be speaking about multiple realization. And the problem, of course, is that if they're performing their function in very different ways, using a very different mechanism, then you can't straightforwardly reduce this functional property of acidity to some kind of microstructure. So it would go against the whole reductionist program.
So different mechanism is decided by physics, is that right?
Not necessarily. It can be decided by chemistry here.
And is that notion absolutely clear?
I think in this case it's pretty clear, yeah. But of course, yeah. In some cases, it has to be worked out in much more detail. I think, yeah.
Now we have Hasok and then Klaus from the audience.
Yeah. Thank you, Pieter. Very clear analysis. Just trying to think about whether multiple realization is the best framing for this debate, right? Because you think about multiple realization as what the mind talk about it, it's sort of the opposite direction of what you're looking at. Because you're thinking about the multiple realization or unique realization over microstructure, right?
Yeah.
In something else. But if the philosophers of mind are thinking about how is anger or knowledge realized at different systems, that's the realization of an observable property in various microstructures.
Yes.
And you're thinking about the realization of a microstructure into.
No, I'm thinking. So yeah. Let me try to clarify it, and hopefully that shows that the two I think are similar. And I think that's what Alex Manafou had in mind when he's the one who actually explicitly uses the term multiple realization. That's why I entertained it here as well. I think. To take acids to be functional kinds, it would be better to describe their function, maybe not in the way I did here as having to donate protons or accepting electrons, but the function of an acid is to turn indicators, colors, to react heavily with metals, to maybe taste sour, whatever. Yeah, those kind of stereotypical properties that have been there all along. And the claim here would be that, well, a lot of substances are able to exhibit this kind of stereotypical behavior, but interestingly so, it's not because they don't all perform that function the same way. It seems that some do so by donating protons, that is by having a microstructure that has acidic protons in it. whereas others do so by accepting electron pairs, that is, by having empty orbitals that can accept electron pairs. And so it seems that there are different microstructures that are able to realize the same kind of stereotypical behavior. Hence, there is a case of multiple realization here. And my claim has been that, well, actually, when you look at those mechanisms that are in play in order to exhibit the stereotypical behavior, they're actually fundamentally the same. They may look different at first sight, but when you look at it more closely, whether it's donating a proton or accepting an electron pair is actually the same thing. I don't know if that helps. Yeah, thank you.
Okay, and finally, Klaus, we are listening to you.
Unfortunately, I could not hear what Hazak was saying. Maybe I'm just repeating some things. I got two questions, Peter, for you. The first, what would you say if I that refers to Marabel's talk? If I would say Brønsted is about naturalness, is sort of referring to natural kinds, and Lewis obviously not. That would be the first question. What would you say to that? And the next one would be operational. What about the problem of the non-possibility to measure Lewis assets as Lewis assets?
Yeah.
You cannot measure them.
Yeah.
What about that?
Yeah, thank you, Klaus. Let me maybe try to answer both questions at once. The worry I have after having written this that may undermine some of the claims I've made is that, and I think you raised it already in your paper, is that Lewis may be overgeneralizing the concept of acidity and may actually start including substances into the acid category that wouldn't naturally be taken to be acids. And I think Tantillo and Seaman go even further because they admitted at some point we're going to start including substances that no chemist would ever call an acid into our acidity category. So that's an overgeneralization of the acidity concept beyond recognition. And to be honest, at this point, I'm very undecided about how serious of a threat this is, because I think substances like carbon dioxide or boron trifluoride, a lot of these substances were taken to be acids already back in the old days by chemists. They knew they had acidic, that they could exhibit acidic stereotypical properties, but clearly those are not Brønsted acids. And so we needed Lewis's theory to understand why carbon dioxide or why boron trifluoride can actually behave in very much the same way as hydrochloric acid or nitric acid. And so it feels to me as if we do need Lewis in order to somehow, collect all the acids together. But I do see the threat that perhaps we're going to start including too many of them. And so I don't quite know where we are there with Lewis.
Okay, thank you. Who else? Eric, please, yes.
Just a brief comment to something Klaus just raised, which namely that Lewis acidity cannot be measured. I believe it can through the use of equilibrium constants. When Fe3+ ions react with 6 water molecules or 6 ammonia molecules, you can measure the acidity, you can measure the degree of that reaction through the well-known stability constants. So this idea that you can't measure Lewis acidity, I think it doesn't work. You can measure it. It is regularly measured. So what's your comment on that, Klaus? If that's not taking us too far away from
I'm sorry about that, but this is nonsense. Of course,
well, I didn't want to use the word nonsense.
I'm sorry about that, but you can measure many things, many substances in this world, of course. But just I'm just asking, why do we call this acid then? I can just measure everything and call it acid, yeah, or what?
Well, if you're limiting the definition of acid to only Brønsted and Lowry, then you're stopping the conversation there, and good luck to you. But
no,
chemists regularly
I was just saying Lewis is really useful, of course, But just to be honest, in the laboratory, we are calling this Lewis acid and Lewis basis. We are not looking for acids if we say Lewis acid or Lewis basis. No?
I think Sidgwick proposed the term acceptor and donor rather than acid and base. So yeah, the discussion started with Lewis. I think something interesting happened with Lewis's introduction, for sure.
Yeah, the only things that the Lewis acid lacks is the presence of H+ ions. But you don't have to have H+ ions for acidity. So what you're getting at is not being able to measure pH, right? But
Ask
if
the
there is no
biochemists.
H, how can you measure pH?
Ask the biochemists whether they use a Lewis theory. Not at all. If they are talking about acids. I mean.
Okay, thank you so much, Peter. Very nice.
Thank you.